All right, in this video, we're going to talk about now the divergence theorem. So the divergence theorem is to surface integrals, what Green's theorem is to line integrals. So if you remember, I mentioned it in the last video, and I obviously mentioned it when we talked about Green's theorem. But Green's theorem was an opportunity for us to take a closed region, and instead of setting up multiple integrals and adding them all together, we're actually able to compute this in one single setup. Now, the divergence theorem is essentially going to do the same thing for surface integrals. And in the surface integral video, the last example I worked is one where we had to compute two different surface integrals and add up the results. And so now we're going to be able to do this all in one step. And so this is actually this setup here that you can see, the triple integral d divergence of f dv is going to give us the outward flux. So this right here is going to give us the outward flux for the situation that we're given. Now, something new about this is the divergence of f. So the divergence of f is going to be defined as the gradient dot f. And on the last video, we talked about the curl, and that was the cross product between these two things. The divergence is going to be the dot product between the two. And so if we let our gradient be partial x, partial y, partial z, and we dot it with our traditional f, which we've been using p, q, and r, then that divergence is going to be partial p, partial x, plus partial q, partial y, plus partial r, partial z. So this right here would be the only thing necessary to drop in right there. Once we drop that in, then it's going to be a pretty standard setup with your dv and of course your triple integral. All right, so the example that we're going to work might look familiar to you. This was one of the ones we did in the surface integral video, and we're going to show that using the divergence theorem, you do in fact come up with the same result. So in this particular case, we've got f being given as this, and then our solid is going to be bounded by these two things. This was that cone and the plane. To kind of clarify a little bit, if you will, I'll sketch in the picture briefly as to what we drew last time. So there's our cone right there. There was our plane. I mentioned an upward pointing vector there and a downward pointing vector there. We had to take that into consideration when we put together the gradient g. So that's the same example that we're taking a look at right here now using the divergence theorem. But for the divergence theorem, all we need to do is find the divergence and then set up the triple integral. So the divergence of f, just like I pointed out in the last slide, is going to be partial with respect to x, partial with respect to y, partial with respect to z, and then of course added it all together. Now I need to erase that because a dot product is not a vector. So we'll have our 2x plus 4y plus 6z for the divergence. So then I'll drop that in, 2x plus 4y plus 6z. At this point now, we would have our dv out there. And so when it comes to getting this thing set up, what I would recommend is, having been given this right here, it's probably not a bad idea to start with your dz. And I'm going to leave that alone for a second, noting that our top would of course be the 3, and our bottom of course would be this x squared plus y squared. Now the other two are going to now drop us down into R2. So we're going to have some combination of dy dx or dx dy or something else entirely. So I'm going to put a dA there, and I'm going to put an r there as kind of a placeholder. If we go back and we take a look here, by letting z equal 3, that's going to give me that circle centered at 0, 0 with radius 3. So my advice when it comes to computing this is to go ahead and integrate as usual right here. And I'm going to leave now the double integral r set, and then integrate this guy with respect to z. That's going to give me a 2xz plus 4yz, and then this will turn into a plus 3z squared, and then evaluate from root x squared plus y squared to 3 with our dA. So as you then go ahead and plug this stuff in here for z, you'll be down entirely to x's and y's. Once you get down entirely to x's and y's, I would probably then convert over to polar for the remaining two integrals. So let me go ahead and plug that stuff in. If I plug the 3 in, that's going to give me a 6x plus 12y, and then plus 27, and then minus a 2x, square root of x squared plus y squared, plus 4y, square root of x squared plus y squared, and then plus 3 x squared plus y squared. With our dA back there, I'm just going to leave it as is for a second, and then go ahead and start converting from x's and y's into r's and theta. So I'm going to go ahead now and slide this up a little bit, and as I get this set up, remember x is going to be r cosine theta. We're going to have plus 12y, so r sine theta plus 27 minus 2r cosine theta times an r, because this is r squared. Square rooting it's going to give us the r. Then we're going to have plus 4r sine theta times an r, and then plus 3r squared. Now, again, that looks kind of like a mess, but it does clean up a little bit, and I do think it's probably going to be easier than using the rectangular coordinate system to put together the bounds on this circle. At this point now, I can drop in an r dr d theta, go from 0 to 3, 0 to 2 pi, and I'll have my final answer. And in fact, if you choose to continue this out, you'll end up with the exact same thing we ended up with when we did it a couple videos ago when talking about surface integrals. So the two big things that I wanted to point out in this particular, three big things I suppose, is that you do in fact get the same result, right? Thank goodness. Then getting the setup done the right way, which in our case was simply the divergence of F, pretty straightforward there. And then in this particular one, I don't know that I've ever pointed it out to you, but there's nothing that says you can't work one iteration in one coordinate system and then convert to another on the next one. And that's something I would certainly want to do here if I was working this one out by hand. And so it's worth pointing out.